Here's the question that I posed at the end of the first part of this video lecture. So, which is the most correct representation of the situation? Well, we know that whenever we bring a charged object close to a neutral object, the neutral object should be attracted toward the charged object. But B and D both show situations where the ball is being repelled from the rod, and so those can't possibly be right, and you can look at them in more detail and decide what else is wrong with them. Then look at A. A can't be right, because the positive charges in the rod should be attracting the negative charges in the ball, and so the negative charges in the ball should be pulled towards the rod. But A is showing them pushed away to the far side, so that's not right. And so we're left with C, where the negative charges are being pulled towards the rod, and as a result, there's a large attractive force between the negative charges and the rod, and a smaller repulsive force that the rod is exerting on the positive charges in the ball. Here's another example of polarization. This metal rod is sitting on top of a plastic container just because the plastic is an insulator, and so this is isolating the metal rod from ground. And here again is a ping pong ball covered in aluminum foil. And I'm going to charge the plastic rod and bring it close to one end of the metal rod. Now note, this charged plastic rod is negative. And so what it is doing to the metal rod right now is polarizing it. And so the metal rod will be negative at this end and positive at the end closer to the plastic rod. These negative charges now are able to attract the metal ball, just like any charged object can. And so if I repeatedly move the rod close, I can get the ball swinging more and more, just like pushing a swing repeatedly in time with its swinging. Polarization just refers to separation of charge within an object, and it's a very common phenomenon. Anytime a charged object is brought close to any other object, it'll tend to polarize that object. Note that conductors are more easily polarized than insulators. I've only shown you how to polarize conductors. I haven't explained polarization in insulators yet. I will in a moment. On molecular scales, polarization is very common, but it's rather different. Molecules are often permanently polarized. You're probably already familiar with the fact that a water molecule is polarized. But this is quite different, because what we've been seeing is how charged objects will polarize neutral objects. But here we have an object which is polarized without any other charged object interacting with it. If you watched very closely when I was charging a metal ball with a plastic rod, you might have noticed something a little bit confusing. Let's have a very close look, because now we can explain it. At first, the ball is attracted to the rod. That's easy to explain now. We know that the ball is being polarized by the rod, and that results in an attractive interaction, as we've seen. Then I touch the rod to the ball. Now the ball is repelled from the rod. That's also easy to explain. They have like charge, and so they repel each other. But watch what happens next. The rod is touching the ball again. The ball seems to be attracted to the rod again. But how can that be? They have like charge now. The explanation, though, is that the ball is charged. However, when it gets close enough to the rod, it also becomes polarized. So even though it has a net negative charge, if it gets close enough to the rod, that charge can mostly be distributed over the far side of the ball, and so the interaction can still be attractive. However, as I rotate the rod, as you'll see me do, I bring new charged parts of it in contact with the ball, and more charge gets transferred to the ball, and again the ball is repelled. The reason I bring this up is that it's just important to realize that it is possible for something to be simultaneously charged and polarized. The explanation that I've given for attraction of neutral objects to charged objects really only works for conductors. Let's review it and then go on to explain how this works in insulators. The electrons in a solid conductor are mobile, and so when an object that's charged is brought near to the conductor, the electrons move to one side of the object. Now, one side of the object is more positive and the other side is more negative, and as we've seen, this results in a net attractive force. What about insulators? In an insulator, the electrons aren't mobile within the object. However, the atoms themselves can still be polarized. When an atom is brought near to a charged object, such as a negative ion, the atom will become polarized. It will experience a net attraction towards whatever charge it was that polarized it. When an insulating object is near a charged object, then each atom in the object becomes polarized, and each atom is then attracted to the object that polarized it, and so the insulator as a whole experiences an attractive force. Let's finish the video lecture up with something that's a bit of a challenge both to demonstrate and to understand. I am charging a glass rod using a piece of vinyl, and you haven't seen this done before, but I'll just tell you this glass rod right now is positively charged. As expected, the ball is attracted to the glass rod, but now I'm going to do something rather different. I'm going to touch the glass ball. In fact, I'm going to hold on to it, so my fingers are in contact with it. I'm now going to bring the glass rod very close to the metal ball, but I'm not going to touch it. Watch. Let's see that again a little more slowly, so that you can see that I pulled my fingers off, leaving the glass rod close to the ball, and then removed the rod. Now, what is the charge on this ball? You might think nothing could have happened because I didn't touch it with the rod at all, right? But now I'm going to charge up a plastic rod. This plastic rod will be negatively charged, and watch. It quite clearly repels that metal ball, so the metal ball is now negatively charged. Some of you watching this video are probably a little confused right now. How on earth, when I was using a positively charged glass rod, and I didn't even touch the ball, how did I give the ball a negative charge? Well, this brings together several of the ideas we've just looked at, and that's why I wanted to do it. So, I touched the metal ball, and so that means that it had a connection through me to Earth. So here's a diagram showing me connecting the ball to Earth. Well, that's grounding, and what I've just done here is the grounding symbol. And remember that what that means is that there's a large quantity of both positive and negative charge available to be shared with the ball. So when I bring the glass rod close to the ball, what happens is that some negative charge is attracted into the ball, and the ball becomes negatively charged. Now, if I break the connection, and before the ball can swing over and hit the rod, pull the rod away, I'm left with a negatively charged ball. This is called charging by induction.